Hello and welcome to our video where we'll be discussing energetics and coupled reactions. When we look at ATP production, which if you haven't already, I encourage you to check out our videos on glycolysis, Krebs, beta oxidation, and the oxidative phosphorylation process. As we looked through those processes, there's an awful lot of specific information to be gathered from them. But at the same time, sometimes you can miss the forest for the trees. If we take a step back, we see a general trend throughout all of those processes where we wind up exchanging energy from one form to another. We take glucose as a high energy molecule, we break it in half, we produce 2 molecules of pyruvate. But we exchange the energy that we got from glucose directly into a couple of molecules of ATP. And as we go through the other processes, we get this continuous trade-off of using one high energy molecule to produce another. So the energy produced from one reaction is used to drive another energy consuming reaction. This has to be true because we have to stay with our laws of thermodynamics. The first law of thermodynamics is going to state that energy is neither created nor destroyed, only transformed from one form to another. So we don't expect energy to magically appear from any one source. If we want to get energy, we have to convert it from a previous form of energy. Also, we have to stick with our second law of thermodynamics. It's the law of increased entropy, which basically states that if left to its own devices, things tend to become more and more and more disorganized. A large molecule with a lot of different subunits tends to break down into its individual pieces. So if we want to create a structure in the body, like a protein, for example, it's a more organized structure than the sum of its individual amino acids. That more organized structure is going to take an input of energy, of which it has to come from another source. We can break these reactions down generally into energy-producing reactions or energy-consuming reactions. And these energetic diagrams are a good example of how we can distinguish one from the other. On the left, we have an energy-producing reaction, an exergonic reaction. We see up the vertical axis is our degree of energy. The higher on the axis we go, the more energetic the state is. Along the horizontal axis, we have time on which the reaction takes place. So here we see our reactants are at this energetic state. Our products are at a lower state. Based on our first law of thermodynamics, energy can't be created nor destroyed. That means that energy, as we went from a high state to a low, that remaining energy had to be released from this system. Conversely, we look at an endergonic reaction or an energy-consuming reaction. We start with reactants. The products are at a higher energetic state once we're all said and done. This required energy to be put into this system in order to create those more organized molecules. ATP is going to be produced by the coupling of ATP-producing reactions, which is an endergonic reaction, with other exergonic reactions. So right off the cuff of this video, I mentioned breaking down glucose to produce ATP. One exergonic reaction combined with one endergonic reaction. So the energy from one is used to drive the other. And we'll see this generality as we flow through this diagram. We look at an exergonic reaction, the breakdown of a high energy molecule like glucose, and the endergonic reaction, as in the process of creating a more organized structure, like an ATP molecule or a protein. So we generally get a net exergonic reaction as we go from glucose, we break it down to produce ATP. Then we can take that ATP, bring it to a ribosome, and use the energy in the form of ATP, break it down to produce a long-chain protein, for example, from its individual components. So we're always looking to trade off high energy into another system and shuttle it back and forth as we pair up these reactions. So that's where the concept of coupled reactions come from. We pair them up. One exergonic driving another endergonic. And then we can take that product and break it down again to release its energy to go into a different reaction system altogether. I want to thank you for watching. Hope it helped. Use this concept as an overall theme for all of the different biochemical pathways like glycolysis and Krebs and oxidative phosphorylation that you've viewed so far. Thank you.